Hi, I'm Taro Kakinuma from Kagoshima University, Japan. My talk is about numerical simulation for tsunamis due to a landslide. This work is done in collaboration with Dr. Iribe, University of Ryukyu, Japan. Tsunamis can be caused by not only submarine earthquakes, but also other various phenomena such as meteorite fall, volcanic eruption, shujubon, landslide or sector collapse, submarine eruption, etc. Today, we focus on tsunamis due to a landslide or sector collapse. This site is here in Japan, and here is Mount Mayu. In 1792, the tsunamis due to a landslide at Mount Mayu traveled Ariake Sea, resulting in tsunamis over 10 meters in tsunami height. This photo shows the seaside slope of Mount Mayu, and the opposite side of Ariake Sea was severely damaged. In another example, this site is here in Japan. This photo shows one of the huge boulders at Ishigaki Island, Japan, where the tsunami is supposed to be a landslide tsunami because the earthquake was not strong. Dr. Iribe in the photo is 1.71 centimeters tall. No, 1.71 meters tall. Such tsunamis due to a landslide are generated through an interaction between water motion and falling bodies, such that the tsunami generation process is rather complicated. To study complicated phenomena, experimental studies are effective. These are part of experimental studies. Landslide tsunamis have also been investigated by numerical calculation. In the present study, we use the numerical model developed by Iribe and Nakaza, 2011, based on the moving particle semi-implicit MPS method designed by Koshizuka and Oka, 1996, to consider furious wave water motion in the vertical 2 dimensions. And we also perform hydraulic experiments where the falling object is water or a group of rigid cylinders. We use a hydraulic basin with a gate on a slope. I'll show you a video of using this basin. By lowering the levers, you can quickly open the gate. Again. Currently, the basin has been extended to 4 meters. This is the sketch of the basin. We set 3 wave gauges and obtain the water surface displacements eta. In the first case, the falling object is water, and the initial height of the falling object, h sub s, is 0.15 meters. The slope gradient beta is uniformly 45 degrees. These are the wave gauges here. second wave eliminated. Again. On the other hand, we generate numerical simulation using the NPS method. Place a glass of water on the table, cover the glass of water, and turn it over. We should not do this in a restaurant. When you take the glass up, the water moves like again. The NPS method is a gridless method, so it's suitable for such furious motion. In the present case, the distance between the particles is 0.5 centimeters, and the total number of the particle is 17,000. The influence radius of the particles is 1.05 centimeters. Let's see the animation of the tsunami generation caused by the falling water. The second wave is also generated by the reflection at the slope. Again. These figures show the comparison of the water surface displacements at wave gauges 1 and 2. The blue lines show the numerical data through the NPS method, and the red lines show the corresponding experimental data. We can see high accuracy, especially in the peak values of the first wave. The numerical results for the phase and the wavelengths of the first wave is also good. I'd like to move on to the next case. In the second case, we studied tsunami generation due to a group of falling rigid bodies. We can see colorful rigid bodies loaded here. These are cylinders. The material is polytetrafluoroethylene, and the diameter is 2.0 centimeters. The length is close to the inner width of the basin. The density is around 2,300 kilograms per cubic meter. Again. I should mention the reproducibility of the experiments. When the falling object is water, we can see a good agreement between 3 experimental data. On the other hand, when the falling object is a group of cylinders, also in this case, the results of the 2 experiments are in good agreement. I'll show you the animation using the NPS method. This figure shows the initial state where the gray objects are the rigid bodies. Each circle or each approximate circle is composed of 12 particles. The animation is again. Shown in this figure is the comparison of the water surface displacements at wave gauge 1. The blue line shows the NPS result and the red line shows the corresponding experimental result. There is a difference in the phases of the first peaks. And this figure shows the results at the wave gauge 2. there are two possible causes for the difference. One is approximation accuracy for the rigid bodies. If we use more particles for each rigid body, the accuracy of shape and force will increase. The other is consideration of friction. We do not consider friction, but if we consider friction, the accuracy of the fall of the rigid bodies will increase. In the last case, we calculated tsunamis due to rigid bodies. This figure shows the water surface displacements at x equals 0.6 meters. The blue line shows the result for the case where the still water depth is 0.09 meters. And the red line shows for h equals 0.245 meters. So the blue is the shallower case and the red is the deeper case. The density of the falling bodies is 2,600 kilogram per cubic meter and the diameter of the circles is 2.0 centimeters. The tsunami height near the shoreline does not depend much on the still water depth. On the other hand, this figure shows the water surface displacements at x equals 2.15 meters. This location is farther from the shoreline. The tsunami height is larger when the still water depth is shallower, because in the shallower case, the tsunamis are hard to disperse, and the tsunami height increases owing to shoaling. Rigid bodies moving on the seabed grow the tsunamis. Conclusions. The tsunamis due to landslide was simulated using the MPS method. When the falling object is water, the MPS result and the experimental data were in good agreement. And when the falling objects were the rigid cylinders, the accuracy of the MPS result was decreased. At the distance from the shoreline, the tsunami height was higher when the still water depth was shallower. Thank you for your attention. Thank you.